In our regular computers, when you think about heads or tails, we can actually think about heads as 0 and tails as 1. And that allows us to think of this whole process in terms of regular computing, binary digits, bits, which are either 0 or 1. What's different about a quantum computer is that we can expand that framework. So the quantum computer can manipulate not just 0 to 1 and 1 to 0, but it can use quantum techniques to create what we call superpositions of zeros and ones, which is really about the quantum bit not just being a 0 or a 1, but having some probability of being a 0 and some probability of being a 1. So it seems like that's kind of uncertain and not really very good for doing precision computing. But this idea of being in this fluid state of 0 and 1 is kind of like thinking about a liquid where you maybe have some, two different colors and you swirl it together so that you have, let's say, red and blue all mixed up together. And what's really magical about quantum is that the computer can mix up the two fluid states, 0 and 1, and the colors in this metaphor. But at the end, what's magical is that the quantum computer can actually separate out the fluids perfectly and create whichever color it needs to win the game. And that part is what sounds magical. But it turns out that there are properties of actual quantum particles like photons and electrons where it is possible to do this. When you have a quantum particle like an electron or a photon, we want to be able to control all of its properties individually and then make each of these quantum particles or quantum bits, qubits is what we call them. Each qubit, we want to be precisely controlling and somehow manipulating it to interact with the other qubits in order to do whatever calculation we want to. In order to do that, there are ways to connect these particles through various kinds of interactions, like magnetic interactions, electrical fields, and electrons have charge, for example, photons have polarization properties. These are the kinds of properties of these particles that we can manipulate using magnets and all of our technologies that we already have existing, but we have to do it at an individual precision level, which is very hard. And at the same time, as we try to make these qubits connect to each other, we also don't want them to be interacting with anything else that is not a qubit. Because when the qubits connect with each other, they form this wonderfully interconnected state that we call entanglement. And that kind of powerful connection between all the different qubits is actually more of a resource than we currently have in our regular computers. So entanglement is a good thing. When the qubits are talking to each other, we can harness that to speed up our calculations. But the problem is that if qubits can get entangled with each other, they can also get entangled with things outside of the computer, such as some perhaps passing stray particle in the universe, and they go and talk to that and get entangled with that. That's what we call noise. It destroys the quantum computer itself, meaning the computing will not work.